We are presenting the paper, A Systematic Approach to Enhancing Scalability and Flexibility in Software Systems. A brief overview of the paper. It talks about the transition from monolithic architecture to microservices architecture and how it improves scalability, agility, and robustness. It also introduces the monolith to microservices decomposition framework, M2MDF. It analyzes of existing decomposition approaches, tools, and its methods. It identifies the metrics dataset used to evaluate and validate monoliths to microservices decomposition processes. The author also proposed area for future research of monolithic to microservices. The focus of this presentation will be on the M2MDF framework and how it helps alleviate common issues encountered during and after the monolith to microservices migration. So what's the purpose and functionality of the M2MDF framework? It assists in decomposing the monolithic architecture into microservices by providing a structured framework. So it enhances scalability, maintainability, and deployment efficiency of the software systems. Some of the key features is that they introduce systematic decomposition approach, which we'll be mentioning later. Integration of various data collection and analysis tools. It also defines phases for streamlined transformation, which we'll be also talking about later. So what problem and questions does M2MDF and migration to microservices address? So the common issue encountered in monolithic system are the scalability issues. M2MDF addresses it by facilitating the division of monolithic system into independent scalable microservices. This allows for more granular scaling of each service depending on the demand and demand at the time. It also addresses the complication in maintaining and updating large code bases. The framework simplifies maintenance and updates by segmenting large monolithic code bases into smaller, more manageable microservices. It also reduces the complexity associated with changes to the code base and deployments, leading to fewer errors and reduced downtime. So what software engineering question does it answer? It answers the question how large complex systems can be efficiently broken down into microservices. And it answers the question what metrics effectively measure the success of a decomposition. The framework highlights metrics such as coupling and cohesion levels, service independence, performance improvements, and deployment frequency as effective indicators of successful decomposition of the monolithic architecture. So what are the M2MDF phases and overview of its importance? So phase 1 is input collection. It involves gathering all the necessary data from existing monolithic system to inform the decomposition process. It collects static code data, dynamic execution data, and any existing documentation that outlines the system behavior and current architecture. The second phase is the monolith analysis. In this phase, the collected data from the previous phase is analyzed to understand the monolithic system structure and dependence. Techniques such as static and dynamic analysis are used to map out the components and their interactions, which helps identify service boundaries. In phase 3, microservices identification, this phase focuses on identifying and defining potential microservices based on the insight gained from the previous phase. It involves applying business and technical criteria to delineate services that can function independently, ensuring that they are cohesive within and loosely coupled. between each other. Phase 4 is the microservices optimization. In this phase, once the potential microservices are identified from the previous phase, this phase aims to optimize these individual services for performance, scalability, and maintainability. They use techniques like refactoring and re-architecturing to enhance the service granularity and optimize resource usage. And in phase 5, microservices evaluation. This phase evaluates the designed microservices against a set of metrics to ensure that they align with the desired quality attributes, such as scalability, reliability, and maintainability. Evaluation can involve simulations, testing frameworks, and pilot deployments. And in the final phase, the microservices deployment phase, this phase involves deployment of the microservices into a production environment. This includes setting up CI/CD pipelines for automated testing and deployment, configuring service orchestration, and ensuring that the services can be monitored and managed effectively post-deployment. And we'll be going through each phase in more detail and how and what kind of software engineering problem are solved. So in the phase 1 input collection, so as I mentioned before, in this phase, data are collected from the monolithic system, which includes static analysis tools to examine source code and its structure, dynamic analysis tool to monitor system behavior during runtime, and manual collection of existing documentation and system specifications. Each of these methods provide unique insights for a thorough analysis. So the importance of the varied data inputs, such as static and dynamic, the integration of both static and dynamic data is crucial, as static data offers a snapshot of its structure and dependencies, while dynamic data provides real-world operation insights. The combination ensures a holistic view of the system, highlighting not only how components are supposed to interact, but how they actually perform in production environment. In this phase, it ensures comprehensive understanding of the system for accurate decomposition, which is important for effective microservices architecture. The comprehensive data collected in phase 1 ensures a deep understanding of the monolithic system's architecture and behavior, which is crucial for identifying potential coupling points between the services and planning effective microservices. Incorporating both static and dynamic data helps avoid common pitfalls in decomposition, such as service-based alignment with business capabilities or overlooked dependencies that could lead to runtime failures and maintenance nightmares. In phase 2, the monolithic analysis. In phase 2, a combination of refined analysis techniques is applied to deeply understand the monolithic structure. These techniques include dependency analysis to map the relationships between modules, component clustering to group related functionalities, and sequence diagram generation to visualize the flow of operation. This method provides a detailed architecture blueprint that identifies tightly coupled components and potential service boundaries. So, integration and impact of advanced analysis tools. So advanced tools such as dependency analyzer, clustering algorithms, and UML diagrams generators are integrated into this phase to automate the analysis process. These tools significantly enhance the efficiency and accuracy of the identifying logical groupings and dependencies within the monolith. Their use not only speeds up the analysis but also ensures that insights gained are based on consistent and objective criteria, reducing bias in decomposition process. This phase have some improvements in the area of software engineering, which is it precisely identifies the decomposition points within the application. The precise identification of decomposition points facilitates the creation of microservices that are well defined and maintain a high degree of cohesion, or minimize coupling between the services. This strategic decomposition leads to improved system modularity, making the software easier to understand, modify, and extend and scale. This phase also aids in foreseeing potential challenges in integration and operations, allowing teams to devise strategies that enhance system resilience, flexibility in response to changing business needs or technology. Phase 3 is microservices identification. The authors compare two clustering algorithms, two identification strategies, clustering algorithm versus rule-based techniques. So for clustering algorithms, they are employed to analyze structural, functional, and communication patterns within the monolith to identify potential microservices. Techniques such as k-means, hierarchical clustering, and density-based clustering automatically group software components that frequently interact or share functionalities, which suggest boundaries that maximize cohesion within microservices and minimize coupling between them. Rule-based techniques. So for rule-based techniques, they utilize predefined heuristics or business rules to carve out microservices. This might involve grouping components that serve a specific business function while separating those that handle different data concerns. The rules are often based on domain knowledge, ensuring that resulting service align well with business needs and logical service responsibilities. So the benefits of this phase is that it optimizes service boundaries, leading to improved microservice autonomy and reduce inter-service complexity. It improves scalability and flexibility of the microservices, and it enhances the maintainability. In phase 4, we have microservices optimization. Application of the generic algorithms for optimization. So in phase 4, genetics algorithms are applied to optimize the configuration and performance of identified microservices. These algorithms simulate the process of natural selection by generating multiple variations of service configurations and iteratively refining them based on sets of performance criteria. This leads to optimizing the allocation of resources, balancing the load across services, or minimize the communication overhead between microservices. And the benefits of this phase is that it enhances performance and resource efficiency in microservice architecture. It has adaptive service scaling, reduce operational costs, and improve system resilience. In phase 5, we have evaluation of microservices, metrics used, and their importance. Service coupling and cohesion measures the degree of independence among microservices and internal strength of interactions within the service. Low coupling and high cohesion are indicative of a well-designed microservice architecture. Latency and throughput assesses the response time and amount of process requests per unit time. These metrics are crucial for evaluating performance impacts of microservice architecture. Resource utilization. It tracks CPU, memory, and storage usage by each microservice, helps optimize resource allocation and cost. Fault tolerance evaluates system ability to handle and recover from failures, an essential aspect of microservices given their distributed nature. And scalability assesses how well the system can handle increased loads by measuring the ease and effectiveness of adding resources to accommodate any spikes or growth. How this phase contributes to software engineering. It provides a validated and benchmarked results demonstrating the effectiveness of the decomposition, ensures continuous improvements, and supports robust quality assurance. In phase 6, we have deployment strategies, deployment best practice and tools, continuous integration continuous deployment CI/CD, implement CI/CD pipelines ensures that microservices are automatically tested and deployed, reducing human error and streamline updates. containerization using containers like Docker for deploying microservices, ensures consistency across different environments, simplifies scalability, enhancing isolation. Configuration management tools such as Ansible, Puppet, or Kubernetes help manage configuration and deployment across multiple services environments, maintaining consistency and control. Blue-green deployment, this strategy involves running two identical production environments, only one which is live at any time. Switching between these environments during development uh, minimizes downtime and risk. Canary release gradually rolling out changes to a small set of users before full deployment helps catch potential issues early, minimizing impact on all users. This phase helped increase the release velocity of new features and fixes, accelerating the overall software development cycle and responsiveness to business needs. Encourage innovation and optimize performance by leveraging the most appropriate technologies and framework for specific microservice functionalities. Reduce costs and enhances performance by allowing teams to scale parts of a system independently without affecting the entire application.
For the methods used in the research, they commence with an examination of the diverse methodologies employed in their research. These methodologies form the foundation of the comprehensive analysis, combining both qualitative metrics and qualitative insights. They adopted this hybrid approach to ensure a through evolution of software architectures, their transition challenges, and strategies for effective decomposition into microservices. By integrating data-driven analysis with narrative-based case studies, they crafted a research approach that captured the complexity and nuance of software system evolution. Next, we delve into the systematic literature review, or SLR. This rigorous methodology involves a structured process to identify, evaluate, and synthesize all relevant research on a given topic. So, for the purpose, the SLR was pivotal in mapping the landscape of microservices transaction strategies, ensuring that their analysis is rooted in comprehensive and systematically gathered in evidence. They meticulously formally research questions and design a search strategies that spans several databases to cover literature published on this topic extensively. And for the process of the SLR, the SLR process in the paper is detailed and methodical, starting with a predefined protocol that identify relevant keywords and database sources, ensuring a broad yet focused search. Screening of abstracts followed by full text reviews allow them to refine their study section and study selection, applying strict inclusion and exclusion criteria. This slide details each step of the process, emphasizing the sovereignty required to ensure the validity and reliability of the review outcomes. And for the type of snowboarding as a method was integral to their literature research, allowing them to expand beyond traditional database searches. Uh, they employ both backward snowboarding, where they locate references within papers, and forward snowboarding, where they investigate who had signed these papers. This dual approach helped in uncovering a more extensive array of sources, including seminal and cutting edge studies that might have otherwise been overlooked. For the advantages of snowboarding presents distinct advantages in their systematic review. It enhances the depth of, uh, depth and the breadth of the literature pool, enabling them to capture a wider spectrum of insights and perspectives, especially in fields as dynamic as software development, where uh, where new innovations and methodologies uh, emerge repeatedly. Snowboarding ensures that reason and relevant studies are included, providing a richer, more current view of the subject matter. And for the process of snowboarding, the first step is selection of C papers. The process begins with a set of C papers, typically selected from a prior database search or known keywords in the field. These papers are expected to be highly relevant to the research topic. And the second step is citation checking. For each C paper, backward snowboarding involves reviewing the reference list to identify parallel studies that might be relevant. Forward snowboarding involves using citation database like Google Scholars, or Web of Science to identify subsequent papers that have cited the C paper. The next step is called relevance assessment. Each potential new source identified through snowboarding must be assessed for relevance based on predefined inclusion and exclusion criteria. This ensures that the expanding body of literature remains focused on the research questions. The last step is iteration. The process is iterative. Each newly included paper can become a seed paper for another round of snowboarding until no additional relevant paper are found. Other returns diminish to a point where it is no longer efficient to continue. For the limitation of snowboarding, despite its benefits, snowboarding is not without limitations. This slide addresses key changes such as potential bias in the selection process and the risk of circular referencing, which can affect the review's comprehensiveness and objectivity. We discussed the measures taken to mitigate these issues, ensuring a balanced and uh, I mean, representative data set for our analysis. So why SLR? They opted for the SLR due to its ability to provide a systematic, transparent, and replicable framework for research. This method is essential in fields impacted by rapid technological advancements, as it helps in accumulating a body of evidence that supports, supports strong evidence-based conclusions. So here we justify the choice of SLR. highlighting its role in building a credible knowledge base that supports sound decision making and policy formulation in software architecture design. And for other possible methodologies, while SLR serves as the primary research method, alternative methodologies also hold potential. So this slide discusses additional methods like meta-analysis, which could provide a quantitative synthesis of findings. There are studies which could tap into expert consensus and uh, ethnographic studies, which could offer deeper con- contextual insights into the deployment of microservices. Its methodologies could complement the findings of an SLR by adding new analytical perspectives or deeper granularity. Concluding our presentation, uh, we synthesize the main findings from the research, reflecting on the implications for parties and policy in software development. In the paper, they outline future research directions that could further refine and expand their understanding of microservices architecture, suggesting potential study that could address the gaps identified through the um, the SLR. And the main of the author is to foster a researcher, I mean, to foster a richer, pronounced understanding of how best to manage the transition from monolithic system to microservices.